11th physics. Today we are diving into the thermal properties of matter. Okay, thermal properties of matter. We are going to explore the difference between heat and temperature, and more importantly, how heat changes the shape and the size of the world around us. Okay, so before we get into the formulas, I want to tell you a story about a clever trick from the past, the blacksmith trick. Okay, imagine a blacksmith in a village who needs to fit a solid iron ring into a wooden cogwheel. Yeah, already you saw that. So here, iron ring. Yeah. So who needs to fit a solid iron ring into a wooden cogwheel. The iron ring is slightly smaller than the wooden wheel to ensure a tight grip. How does he do it without breaking the wood? He does not use a hammer to force it. Instead, he uses physics. He heats a iron ring in a fire. Yeah, iron ring in a fire. As the iron gets hot, it expands and becomes larger than the wooden wheel. He slips it on easily. Okay, he slips it on easily. Then he pours cold water over to it. Okay, he pours cold water over to it. The iron contracts and grips the wooden wheel so tightly that it never comes off. Okay, so this is a blacksmith trick. So today we are going to learn the science behind this magic, which is actually thermal expansion. Okay, right. So, all right, before we explain why the ion is expanded, let's see what you remember from your previous science classes. I am sharing my screen now with three quick questions. Let's, I'm sharing the screen. Yes. Okay, you got it? Yeah. Which of the following is the SI unit of heat energy? Option A, watt. Option B, joule. Option C, Kelvin. Option D, Pascal. Which of the following is the SI unit of heat energy? Already you knew about that SI units. For heat energy, what is that? Watts, joule, Kelvin, Pascal. Which one is correct? Which one is correct? SI unit for all the energy is option B. Yes, joule. Okay, option B, joule. Very good. Good. Second one, in which direction does heat naturally flow? In which direction? From cold body to hot body, or hot body to cold body? Between bodies at same temperature, it does not flow. Which one is correct? In which direction does heat naturally flow? From where to where, or between at same temperature, or it does not flow? Which one is correct? In which direction does heat naturally flow? Always heat flow from the hot object to cold object. Yeah, hot body to cold body. Yes. Okay. Option B is the correct answer. Okay. And the final one already very easy. You know that. What is the freezing point of water on the Celsius scale? Already you know about that three types of scale: Kelvin scale, Fahrenheit scale, Celsius scale. So freezing point of water: 100 degrees Celsius, 32 degrees Celsius, 0 degrees Celsius, 273 degrees Celsius. Which one is the correct answer for the freezing point of water on the Celsius scale? Celsius scale. Yes. So freezing point of water on the Celsius scale, 0 degrees Celsius. We can see that answer. Which of the following is a unit of heat energy? Joule. In which direction does heat naturally flow? Hot body to cold body or hot object to cold object? What is the freezing point of water? That is on the Celsius scale, 0 degrees Celsius. Okay, clear? Okay, right. So, first we must clear up a common confusion, that is heat with temperature. Heat with temperature. Heat. So heat is a form of energy. Okay, form of energy that flows from a hot body to cold body. Its units joule. Its unit joule. Okay, okay. And on the other hand, temperature. Temperature. So temperature is a measure of the degree of hotness or coldness. Okay, temperature is a measure of the degree of hotness or coldness of the body. So it determines the direction of heat flow. It determines the direction the heat will flow. And the SI unit for temperature, Kelvin. SI unit Kelvin, and temperature determines the direction the heat will flow. Now we measure temperature on the three main scale. Yeah, already you know that: Celsius, Fahrenheit, Kelvin. First scale, Celsius scale, degree Celsius. Yeah, and second one, Fahrenheit. You have to put degree to the Fahrenheit like that. And third one, Kelvin. You don't put degree to the Kelvin. Okay, just to put the capital K. Celsius, for example, freezing point of water, freezing point of water 0 degree Celsius. Yeah, H2O. And boiling point, already you know that boiling point 100 degrees Celsius for water. Yeah, for the same point, that is freezing point and boiling point in Kelvin, and freezing point, that is in the Fahrenheit scale, freezing point FP 32 degree Fahrenheit, and boiling point for the water. Okay, 212 degree Fahrenheit. Freezing point in Fahrenheit 32 degree. Boiling point of water in Fahrenheit 212 degree. Okay, degree Fahrenheit. Okay. In Kelvin scale, there is one important term, that is absolute scale. Okay. So 0 Kelvin. 0 Kelvin called as absolute zero. 0 Kelvin called as absolute zero. Okay, absolute zero. This is a absolute scale, and 0 Kelvin is a absolute zero. And in terms of degree Celsius, it is minus 273.15 degree Celsius. Okay, in degree Celsius, minus 273.15 degree Celsius. Clear? Okay. Now I will write a conversion formulas. Okay. Please note it down. Please see that. Okay. Celsius, Fahrenheit, Kelvin, like that. Now we are going to conversion formulas. First of all, this is means TC means temperature in Celsius. By 100 gives TF. Temperature in Fahrenheit value. Okay. Minus 32 divided by 180. 180. Clear? This is a conversion formulas you need to note down. And in terms of in Kelvin, just add the 273.15. So there are three scale: Celsius scale, Fahrenheit scale, Kelvin scale. Suppose if you have the temperature in Celsius, you just add the 273.15 to get in the Kelvin scale. And for that, in this case, TC, TF. Suppose if you have TC value, put it down and you will get the TF. Suppose if you have TF value, that is temperature in Fahrenheit value, put it here and you will get the TC value. Clear? This is very important formula. Please note it down. Okay. One last thing for the gases, that is pressure, volume, temperature, are connected by the ideal gas equation. Yeah, ideal gas equation, that is PV is equal to mu RT. Ideal gas equation, that is PV is equal to mu RT. This is an ideal gas equation. Clear? Okay. So let's go back to our blacksmith. Why did the ring get bigger? Because most substances expand on heating and contract on cooling. Already you knew about that. Yeah. So most of the substances expand on heating. Most substances expand on heating, contract on cooling. Okay. So we look at this in two ways. First of all, linear expansion. Linear expansion. Linear expansion. So linear expansion is also known as a length change. Linear means length, okay? Length change. If you heat a rod, it gets longer. Yeah, if you heat a rod, it gets longer. So, for this linear expansion, we have a formula as per your book, that is del L by L. Del L by L equal to alpha L into del T. Alpha. Clear? So here alpha L is known as the coefficient of linear expansion or linear expansivity. Clear? Okay. So if you heat a rod, it gets longer. Okay. Del L by L equal to alpha L into del T. Del L means length change. L means original length. Alpha L means coefficient of linear expansion and del T means temperature changes. Clear? Okay. Now volume expansion. Volume expansion. So volume expansion, already know that volume. Yeah. If you heat a block or sphere, its volume increases. Okay. If you heat a block or sphere, its volume increases. Volume increases. Okay. We have a formula for this also, that is del V by V equal to alpha V into del T. Del V means volume change. Capital V means original volume. Alpha V means, that is coefficient of volume expansion. And del T means, already know that, temperature difference. Clear? Okay. So for solids, alpha V, that is coefficient of volume change, is approximately 3 times the coefficient of length change, that is linear expansion. Clear? So alpha V is approximately 3 times the length expansion, that is coefficient of expansion, linear expansion. Clear? Please note it down. Very important relation. Alpha V is approximately 3 into alpha L. Clear? Okay. So this is all for matter. But one expansion is there. Exception. Sorry. That is water. Expansion. For water. For water, it is something change, something different. Okay. It shows anomalous expansion. Anomalous expansion. When you heat the water from 0 degree Celsius to 4 degree Celsius, it actually contracts. It actually contracts. So it has maximum density at 4 degrees Celsius. So water has maximum density at 4 degrees Celsius. Clear? Okay. This is why ice floats and aquatic life can survive in winter, because the bottom of the lake stays liquid at 4 degrees Celsius. Okay. So very important character for the water, that is anomalous expansion. When you heat water from 0 degrees Celsius to 4 degrees Celsius, it actually contracts. It has maximum density at 4 degrees Celsius. This is why ice floats and aquatic life can survive in winter. That is, the bottom of the lake stays liquid at 4 degrees Celsius. Clear? Okay. Now we are stepping into our virtual thermal expansion lab. I will share the simulation screen now. Okay. Okay. So thermal expansion lab to explore how heat energy affects the size of matter. Remember, thermal expansion is simply the tendency of matter to change in volume in response to a change in temperature. Thermal expansion means change in matter, change in size or shape of the matter with respect to temperature. Okay. Look at look down at our simulation. The main variable here, that is temperature, 20 degree, 34, like that. Okay. So we can adjust temperature. You can use a slider to manually change the temperature, moving from freezing point or like that, for example, 0 degrees Celsius or minus 10 degrees Celsius to maximum 100 degrees Celsius. Okay. From freezing pole to and up to the boiling point of water, that is 100 degrees Celsius. Okay. Or you can hit the heat button to watch the simulation automatically. Warm up to 100 degrees Celsius. Okay. So first of all, linear expansion, solids. Yeah. So expansion, linear solid. Expansion in one dimension. One dimension means length. Okay. And volume expansion. Volume expansion, solids and liquids. Expansion in all three dimensions. And finally, water anomaly. The unique way water behaves, especially near freezing. Clear? Okay. First of all, linear expansion, solid. We will start with the linear expansion, which is what happens when a solid material, like a metal bar, here you can see the metal bar, heats up and gets longer. Okay. Now you can see that metal 20 degrees Celsius size there. Yeah, length 100 point degree 0 percentage related to 20 degrees Celsius. Okay. Now increase the heat. You can see the change in length. Yeah. Clear? Yes. So if you increase the temperature slowly by using the slider, you can see that the heat energy causes the particles inside the metal to vibrate more vigorously, pushing them slightly further apart, and the material expands in length. Okay, expands in length. Now let's hit the heat button. Watch the metal bar again. So it goes 100 degrees Celsius. You can see that how much the length has changed. The scale shows us it now about 111 114.4 percentage of its original length. Okay. So the actual percentage is tiny. We have exaggerated it visually to we can study it. Okay. Now use the slider to cool down to 0 degrees Celsius or minus 10 degrees Celsius, like that. Yeah. The bar contracts, becoming shorter than the 20 degrees Celsius reference. So it works in reverse. As we remove heat, the material contracts. Okay. So engineers must leave gaps, expansion joints in bridges and railway tracks. If they did not, the forces generated by thermal expansion on a hot summer day would buckle the steel. Okay. This is why engineers design expansion joints in bridges and railway tracks. Okay, right. Now volume expansion, solid. So we move into the volume expansion. This is simply the linear expansion happening in all three dimensions. That means length, width, and height. Okay. The volume is the total space the object takes up. Clear? Okay. Now let's slowly increase the temperature around 70 degrees Celsius. Yeah. Okay. The cube grows in size. Yeah. Clear? So notice the difference from the linear mode. The object grows wider, taller, and longer simultaneously. Clear? The volume is increasing much faster than the length at 70 degrees Celsius, for example. Okay. So the volume is already around 128.0 degrees Celsius percentage. Yeah. Of the original. That's because if you multiply a slightly longer length by a slightly wider width by a slightly taller height, the total volume increase is multiplied. This principle makes thermometer work. The mercury or alcohol inside takes up more volume as it heats up, forcing it to rise up the narrow tube. Okay. So this principle explains how a traditional thermometer works. As the liquid inside the thermometer heats up, its volume expands. And it gets no choice but to rise up the narrow tube, showing us the temperature. Okay, clear? And finally, water anomaly. Okay, our final and most fascinating mode is the anomalous expansion of water. Water does something unique when it cools down near freezing. Clear? Okay. So normal contraction at, for example, at 20 degrees Celsius, the water volume 102.4 percentage expanding normally like that. Okay, like this is high volume, this is high volume, and 4 degrees Celsius minimum. Okay, right. For example, we are at a 20 degrees Celsius. Slide the temperature down towards 10 degrees Celsius. You can see that the water level drops. Yeah, water level drops. That means it contracting normally, like most material. As the water cools, it contracts and becomes denser. Okay, water cools and it contracts and becomes denser. Now keep the sliding it, pay, paying close attention as you approach 4 degrees Celsius. Here, the scale ruler marks a volume at this point with a dashed line. You can see that. Okay. At 4 degrees Celsius, water has its maximum density. Okay. Maximum density and its minimum volume. Okay. And it is minimum volume. It is as small as it gets. Now keep cooling from 4 degrees Celsius to 0 degrees Celsius and into the negative temperature. Yeah, look, the volume is expanding even though we are cooling it. So at 0 degrees Celsius, and below, the ice structure forms creating crystal lattice that takes up more space than the liquid water did. Okay. So the volume is expanding even though we are cooling it at 0 degrees Celsius and below, the ice structure forms. Ice structure forms. Clear? This anomaly has a huge impact on life because water expands when it freezes. Ice is less dense than liquid water, so ice floats. If ice sank, lakes and oceans would freeze solid from the bottom up, making life impossible for most aquatic organisms. So this anomaly protects life on Earth. Clear? This is an anomalous expansion of water. Okay. So now to creative question related to this topic. Why do thick glass tumblers crack when you pour boiling water in them, but thin Pyrex beakers don't? Why do thick glass tumblers crack when you pour boiling water in them, but Pyrex beakers don't? Thick glass has poor conductivity. The inner layer expands before the outer layer, causing stress. But the Pyrex has a low coefficient of expansion. Already you know that alpha or alpha L. Okay. So generally alpha, low coefficient of expansion. So it does not change shape as much. So Pyrex beaker is best for this type of a case. Okay. Second one, how does an automatic fire alarm work? Automatic fire alarm work. It uses a bimetallic strip. Bimetallic. Bi means two. So two metals with different alpha, different coefficient of expansion. So heat makes it bend, completing the circuit and ringing the bell. This is a very simple reason for that automatic fire alarm works. Okay, it uses a bimetallic strip, that is two metals with different alpha. Heat makes it bend, completeness circuit and ringing the bell. Clear? Okay. Now we are going to the problem. So here you can see that one problem, basic linear expansion. The brass rod of length 2 meter at 27 degrees Celsius is heated to 127 degrees Celsius. Calculate the increase in length, that is alpha brass. Okay, so calculate the increase in length. So we have to find the linear expansion. So given alpha brass, that is coefficient of brass is 1.8 into 10 power minus 5 Kelvin inverse. Okay. Okay. So for the problem number 1, the datas are first of all alpha. Yeah, clear? Alpha. So we can write here brass alpha 1.8 into 10 power minus 5 Kelvin inverse. The brass rod is 2 meter long. 2 meter long. It is long at 27 degrees Celsius. Okay. It is heated to 127 degrees Celsius. Calculate the increase in length. Already we know that the formula. Yeah. Okay. So first of all, del T, you have to find the del T. Del T means temperature change. Already I told you that is final temperature minus initial temperature. 127 minus 27, which gives 100 degrees Celsius. Alpha L, we have a alpha L 1.8. Del L, that is changing in length. So L means original length. So original length 2 meter. So we have to find the del L. Okay, we have to find the del L. This is a increase in length. So for that case, del L equal to alpha L into L del T, because this L goes here and here. Okay, like alpha L 1.8 into 10 power minus 5. L 2 del T 100. You can multiply, which gives del L 3.6, because 1.8 into 2, which gives 3.6. Yeah, and 10 power minus 3 meter, because this is a 10 power square. So 10 power minus 5 and 10 power 2, you know that 10 power minus 3. 10 power minus 3 means millimeter. So 3.6 millimeter. 3.6 millimeter. Clear? Okay. Now, second problem. Problem number 2. Railway tracks are laid using steel rails for length 25 meter each. If the tracks are laid on winter day, when the temperature is 15 degrees, that is 15 degrees Celsius, what is the minimum gap that must be left between two rails to prevent buckling during summer when the temperature rises to 45 degrees Celsius? Coefficient of linear expansion for steel 1.2 into 10 power minus 5 Kelvin is. Okay, this is a constant value. Already you know that. So here railway tracks laid using steel rails. Okay, length 25 meter each. Winter day, the temperature is 15 degrees Celsius. On a summer day, temperature rises to 45 degrees Celsius. So you have to find the minimum gap that must be left between the two rails. Okay. Okay. So for this sum, we have a data. Problem number 2. We have a data. First of all, del T 45 minus 15. Yeah. Okay. Because summer day and winter day temperature. 45 minus 15 gives 30 degree Celsius. Okay. So you know that formula del L is equal to alpha L L del T. Alpha L, that is alpha steel, 1.2 into 10 power minus 5 Kelvin inverse. L, that is original length, 25 meter. And finally, del T, 30 degrees Celsius. Clear? So you will get the 9 into 10 power minus 4 meters. 9 into 10 power minus 4 meters. So which is also known as 0.9 millimeter. This means we must leave at least 0.9 millimeter gap. Okay. Okay. The gap. So the sum is, what is the gap needed to prevent buckling? So we must leave at least 0.9 millimeter gap to prevent the buckling. Clear? Okay. Now let's see how will you grasp the concept. I am sharing my screen for the 5 question MCQ. Again, I am sharing the screen now. Okay. Right. What is the value of absolute zero on the Celsius scale? First question. What is the value? What is the value of absolute zero on the Celsius scale? Already you know that absolute zero in Kelvin. And you know about the conversion formula between Kelvin and degree Celsius. So what is the absolute zero on the Celsius scale? 0 degree Celsius, minus 100 degree Celsius, minus 273.15 degree Celsius, and finally minus 459 degree Celsius. Which one is correct? What is the value of absolute zero? Yes, good. Option C. Very good. Anybody? Option B. Okay. Which one is correct? Option C or option B or option D or option A? Any other students? Any other responses? Which one is correct? The value of absolute zero. Option C. Okay. So we can choose option C. Okay. Second question. The coefficient of volume expansion is approximately how many times the coefficient of linear expansion? Already I told you there is a relationship between the volume expansion and linear expansion. Alpha L, alpha V. How many times? Very easy one. Yeah. C. C. Okay. So alpha V is approximately 3 times the alpha L. Clear? Okay. Water has maximum density at. Water has maximum density at. Yes, very good. Clear. Yes, good. That is, yeah. Yeah, option C is the correct answer. Very good. 4 degrees Celsius. Water has maximum density at 4 degrees Celsius. Good. Pyrex glass, already I told you, is used for cooking vessels because it has a option A, high specific heat. Option B, low coefficient of expansion. Option C, high boiling point. Option D, high density. Pyrex glass is used for cooking vessel because it has good. Option B or option C? Someone told low coefficient of expansion. Someone told high boiling point. C, Pyrex glass. So which is different from normal glass because Pyrex glass having a has one important characteristics. What? C or B or A? High boiling point. Okay. So okay, let's choose option C. We can see that answer, but it is a wrong answer. Yeah. Okay, good. And the final one, which equation represent the ideal gas law? Which equation represent the ideal gas law? B, C, B. Good. Yeah. Yes. Good. Correct. APMS, KGBP, MSM, GG. Yes. Good. Good. Yes. So very clear about that. Yeah. PV is equal to mu or T. Clear. Okay. Now let me check the answer. What is the value of absolute zero on the Celsius scale? That is minus 273.15 degrees Celsius. Already I told you 0 Kelvin. So Kelvin degree Celsius means you have to add the 273.15 to the degree Celsius to get into the Kelvin. Suppose if we have the Kelvin, just subtract the 273.15 to get the Celsius. So 0 minus 273.15 gives minus 273.15. That's why this is an absolute value, absolute zero value in the Celsius scale. Okay. And second one, already you know that coefficient of volume expansion is 3 times the linear expansion. Yeah. And here also, water has maximum density. Yes. Already you all told that there is 4 degrees Celsius. Okay. But in terms of Pyrex glass, is used for cooking vessels because it has a no, no. Okay. No high boiling point answer. Okay. So it has a low coefficient of expansion compared to the normal glass. Pyrex glass has a low expansion, a low coefficient of expansion. Clear? Okay. And the final one, which equation represents the ideal gas law? Yeah, PV is equal to mu RT. Yes, correct. Good. Clear? Okay. Right. So now summary. Heat is the energy. Yeah. So temperature is the degree of hotness. Degree of hotness. Solids expand in length and volume. Okay. Solids expand in length, that is alpha L and alpha V. Okay. Water maximum density at 4 degrees Celsius. Okay, right? Okay. Now homework. I will share the screen again. Please note it down or you can take the screenshot. So this is for your homework. Two homework. One is reasoning, another one is calculation. Please note it down. Explain why telephone wires are left slightly loose between poles during summer. Explain why telephone wires are slightly loose between poles during summer. Okay, okay. Second one, this is calculation related. A steel bridge is 200-meter long at 20 degrees Celsius. If the temperature rises to 40 degrees Celsius in summer, how much will the bridge expand? Very important and easy one. Yeah. So take alpha steel 1.2 into 10 power minus 5 Kelvin inverse. A steel bridge length is 200-meter long. Clear? At 20 degrees Celsius. So if the temperature rises to 40 degrees Celsius in summer, so temperature changes from 20 degree to 40 degrees Celsius. Yeah. A steel bridge 20-meter long and the temperature difference here alpha steel 1.2 into 10 power minus 5 Kelvin inverse. And how much will the bridge expand? Clear? Okay. So that's all for today. Thank you, students. Thank you, all teachers. Thank you all. Jai Bharat, Jai Hind, Jai Vidyasati. Thank you. We will see the next class. Thank you.